started to record, and now we are going to present. Okay. Vivek MG, you stop presenting. Okay.
Yes, sir.
You stop presenting something you are presenting. Vivek MG. Vivek MG.
Sir,
Who's
you
what
can
Vivek
start.
MG is presenting?
Sir, you can start present, sir.
But why it is showing Vivek MG is presenting?
Nothing, sir.
So why you have come over
ಅದು
this? So
ಆಫ್
remove that. Your
ಮಾಡಬೇಕು.
name
Not
should
present.
switch off that.
ಕಟ್ ಮಾಡ ನೀನು ಸ್ಟಾಪ್ ಪ್ರೆಸೆಂಟಿಂಗ್
Hmm.
ಅಂತ ಕೊಡು.
Hmm. Yes.
ಇಲ್ಲಾಂದ್ರೆ ಎಕ್ಸಿಟ್ ಆಗಿ ಇನ್ನೊಂದ್ಸತಿ ಜಾಯ್ನ್ ಅದು.
ವಿವೇಕ್
Okay.
ಲಾಗೌಟ್ ಮಾಡಿ ಲಾಗಿನ್ ಆಗು.
ಎಸ್ ವಿವೇಕ್ ಎಂ ಜಿ.
ಇಲ್ಲ ಅನ್ಸುತ್ತೆ.
Sir, can I make him to exit, sir?
ಸರ್ ಲಾಗೌಟ್ ಆದಲ್ಲಿ ವಿವೇಕ್
You can
ಲಾಗೌಟ್ ಆಗು.
see. Can you see?
Yes, sir.
Can you see the?
Yes, sir. Yes, sir.
Yes, sir.
Yeah.
ಸರ್
Stop.
ನಾನು
Now stop. Okay. So today's class we are going to start with the estimation of operating characteristics. So basically, the operating characteristics of an induction motor comprise of your magnetizing component and your iron loss component. So the iron loss component is based upon the core losses that happen inside the stator teeth, and core can be estimated by what? Respective specific loss per kg of material corresponding to the flux densities in the core and the teeth. And now your magnetizing loss, it comprises, see, magnetizing loss is you are giving supply to your stator, flux gets established in the stator core, it interlinks with the stator teeth. Then after the stator teeth, there is some distance, a gap between rotor and the stator, and this gap is the air gap. And from the air gap, then again this flux gets induced to rotor teeth and finally to the rotor core. So in stator and rotor teeth, flux density distribution is approximated as a sine wave with a superimposed third harmonic, as the actual flux density distribution is flap topped one. What does it mean is that you don't get an sinusoidal curve, like you get a third or harmonic also. So that means you get a frequency, and you get a frequency of 3f also. So but to avoid this third harmonic only, what we have done, we have skivered it, we have chamfered the rotor teeth and the stator teeth. That is means we have cut it at an angle of 45 degrees. Now basically this is the, you can see this pictorial demonstration. Here you can see this is my perpendicular, this is my magnetizing component of the current, and this is my core loss component of the current. Can be clearly seen my magnetizing part of the current is 90-degree out of phase with voltage, and I1 is in phase with voltage. So no load current per phase, you can write I naught, this I naught is equal to, this is like, if you take this as I1, and this perpendicular is same as your IM, you can say this IM and this IM same, this IM. So in this triangle, if you can see this triangle, you can write in this triangle hypotenuse is this, I naught square is equal to, by Pythagoras theorem, perpendicular square by base square. So perpendicular square is how much? Im square, because this is same as Im, it's parallel to the Im and it's in equal in length, plus I1 square. Similarly here cos phi naught, you can say cos phi naught is base by base by what? Hypotenuse. What is base? I1. What is hypotenuse? I naught. So you can say here cos phi naught is equal to I1 by I naught. So this is the magnetizing current. So the flux produced by the stator winding passes through the following parts. So stator winding, it passes through the following path. Number one is your state air gap, your stator teeth, your rotor teeth, your stator core, and your rotor core. So what happens is that what we are see basically there are one that interpolar axis which you have studied in your previous classes in your electrical motors. The value of flux density would mean ba, that is phi by area, at is at 60 degree from the interpolar axis, is the same irrespective of whether the third harmonics are present or not. So what we usually do, we take the flux density at at an angle of 60 degree, because it will remain same compared to any other degrees for our average flux gap density, because your wave is a sinusoidal wave. Whatever current you are giving, it is a sinusoidal current. So let's and the average at 60 degree remains same irrespective of whether the third harmonics are present or not. So hence the calculation of magnetic ampere turns to be based upon the value of flux density at 60 degree from the interpolar axis as far as the gap and teeth are concerned. So we'll consider this, and I will show you mathematically also how why I have taken this. The mmf in various paths is determined as follows. See, what happens is, look at the right side, then we'll go to the left side. First look at this, please pay attention. MMF required for air gap for sinusoidal flux distribution. For example, this is my air gap BG, and I have written BG is equal to the average BAB. So this air gap first component BG1 sine theta. So this is my fundamental. Okay. Then BG3 sine 3 theta plus BGS sine 5 theta. So what we do is we are neglecting the even harmonics because they cancel out. That is 2 and 4 I have not written. I have written 3, 5, 7,
We
similarly
can't
like
hear,
that.
sir.
Huh? You can't hear? Now you can hear?
Yes, sir.
Yes.
It's not audible.
Okay, okay. Now you can hear? Now BG is equal to BG1. Now you can hear?
Yes, sir. Yes, sir.
Okay. So BG, you can see BG is equal to BG1 sine theta plus BG3 sine 3 theta plus BGS sine 5 theta t. So neglecting the even order harmonics, and let's suppose this theta is equal to 60 degree. So only I am taking the first component over here. So my B 60 degree would be equal to BG into sine 60, and my sine BG into sine 60 is root 3 by 2. So B 60 degree would be root 3 by 2 and BG1. Now for sinusoidal distribution, so we have to consider
Yes, sir.
in electrical radians. So we will write
Yes,
that
sir.
B max would be equal to pi by 2 plus BG. So Pradeep Kumar, please shut up, shut your mouth, listen to it, don't interrupt. Is equal to pi by 2 plus root 3 by 2 plus BG. Nobody is going to explain you all this thing. It's not written so clearly in any book. Okay. So B 60 degree would be equal to root 3 by 2 BG1. For sinusoidal gap, what it would be equal to? It would be, you have to take, see, one cycle is equal to 180 degree. You have to take for one half cycle is 180 degree, and the maximum flux will happen at sine 90. So sine 90 happens to be at pi by 2. Pi by 2 electrical radian is 90 degrees. So for maximum average flux density to happen, it should happen at pi by 2 bg, and pi by 2 this 60 degree, pi by 2 this bg. So pi by 2 into root 3 by 2 bg, this value you get b at an angle of 60 degree, you get at 1.36. What is 1.36? 1.36 is pi by 2 into root 3 by 2. If you will multiply, you will get 1.36 bav. Now after understanding this, let's come to this. mmf for air gap is flux density at 60 degree from interpolar axis. This is your BAV into sine 60. So BAV, how much it would be? BA is flux by area into sine 60 is root 3 by 2, and when it will be maximum, it will be maximum at pi by 2, this pi by 2. So you can write your pi by 2 into root 3 by 2 is equal to 1.36. 1.36 is into flux by area is equal to flux by area is equal to your BAV. So 1.36 BAV you are getting over here. So uh, now we'll move to the next part. Is what we are requiring is we require MMF for air gap calculation and the number of turns. Similarly, we will also again we'll consider this. Your ampere turns would be equal to, usually this is from the statistical data, whenever you are designing a machine. So you take a value of 80,000 kg BGO LG, wherein kg is the gap contamination factor, that is the air gap contamination factor. Theta angle is 60 degrees. Theta angle is 60 degrees. This gap contamination factor can be anywhere between 1.05 to 1.15. And then you have your BGO. Of course, you just saw now BGO is 1.36 BAV, and LG is the length of the air gap. Okay. Now you can see this what I have drawn also here. See, this is my stator core. This is my stator teeth. This is the air gap in between, and this is the flux path. So this is yes, in other class also we have studied various factors like diameter, depth of the rotor, diameter of the stator core, and other things. So now let's go for the MMF of stator core, how we will calculate. So the flux density in the stator core, that is BCS, the ampere turns per meter length, acts in as found from the BH curve of the material. The length of the flux path or the stator core is the diameter. Okay, stator. See, this length, or this is my length ICS or LCS. Various books are using. This can be has an empirical formula. This can be derived also, but what I've seen in your examination, derivation of this is not required. 1 by 3 divided by pi plus d plus 2 dss plus 2 dcs divided by p, which I have previously also I have mentioned. This is the number of stator slots, this is the depth of the stator, and this is the diameter of the stator, and these p is the number of poles. Similarly for rotor also same formula will come. Now MMF for rotor core you have same, but only thing is that this will be diameter of the rotor, this is the depth of the rotor, and this is the stator that bar is there of that depth of the rotor core. This is for stator core, this is for rotor core. And this again in the previous formula also we have seen, this is given by, for 1/2 cycle it is given phi m by 2 BCR into L1, wherein this is the breadth and length. So here we have to total magnetizing MMF per pole is given by total magnetizing MMF is, this is for air gap ATG, this is for the stator, this is for the rotor, this for the stator core, this for the rotor core. So these are the 5 terms that are involved when we have to take the total MMF. One will be for normally for stator, another is for rotor, this is for the core of stator, this is for the core of rotor, and this is for air gap. So this total MMF divided by number of turns. Previously also we have, when we were studying the transformer also, we have seen Im is equal to 80 divided by root 2t. Why I am using root 2t? Because ampere turns divided by turns will give you amperes. But why root 2t? Because I'm taking my RMS value. If I'm taking RMS value, IRMS would be equal to Im by root 2. So this is IRMS value. Usually we take IRMS value. Here I should have written IRMS. But usually some books are neglecting, straight away they're writing Im as if it is assumed to be the RMS value. See here also, the peak MMF related to RMS value of Im is, now the peak MMF related to the RMS value of Im is 2.7 Im T phase kW by number of poles, ampere turns per pole. Now you will say, sir, how, from where it is come? So this is also one empirical formula. When we are substituting it, it is a universally it's seen that this is two. This can be derived. It's again 2-3 pages, which is not in your syllabus as far as I'm seeing the derivation part, just like that diameters and all. So this is an empirical, but many numericals have came on this particular topic. So this thing is 2.7 Im T phase kW by P. So where P is equal to number of poles, T phase is equal to number of turns per phase. Kw, of course, you know, is the winding factor, and you can calculate your Im. So usually your Im you can calculate where P is number of poles, T phase is number of turns per phase, Kw winding factor. If you are using for 30°, that is usually this formula is not required, but you can also remember that mostly which formula, mostly we are using, see, 8 80-60 for ampere turns at 60° would be root 3 by 2 into 2.7 Im Ts kws by P. So root 3 by 2 into 2.7, you will get this value of 0.427. Again, Im you will keep here. So Im you are keeping here. So in the down, you will get Ts by Kw. This is the number of poles, 80-60. So this is the formula that you have to keep in mind. This is the formula when you will be asked about how to find the magnetizing current. So you will be using this formula to calculate the magnetizing current. And if somewhere down the line they have given it like this, but this usually doesn't come. So what is the difference between this and this is that here you can see that same thing, sine 60, same sine 60 is root 3 by 2, and this is but you P80 by 30, but you get root 3 by 2 into 2.7. But here you can see where it is, yeah, sorry, here is P80 30°. So you have to substitute here, instead of sine 60 it is 30°. So sine 30 would be 1 by 2. So at that time you will getting this formula, but usually we are not using, if they have mentioned that angle, so accordingly you substitute 2.7 into 1 by 2 you do. Otherwise we know that we have to use this at 60 degrees only, because the interpolar axis and the harmonics are getting eliminated. For better understanding the concept, we'll go to a numerical and try to solve it and understand this
Sir, is it
numerical.
sin 60 or sin 30, sir?
Huh?
Is it sin
Yes, yes.
60 or sin 30, sir?
Sine 60, sine 60.
Okay.
Sine 60 is root 3 by 2. It is not sine 30. That is like this is
Okay, sir. Okay.
yeah. During the, see, listen to me. During the design of a 3-phase 5 kilowatt 400 volt 50 hertz 4-pole squirrel cage induction motor designed for star delta starting, following data has been obtained. Your rotor diameter is 0.14 meter. Your core length is 0.11 meter. Turn per phase on stator is 360. Air gap length is 0.5 millimeter. So you just see, this is in meter, this is in meter, this they have given in millimeter. And your correction gap contraction factor, or that is 1.25. Okay. So now assuming that the ampere turns required for the iron parts are about, this is an examination problem appeared in V2 exam, similar to it 2-3 times. So it's very important. Assuming that the ampere turns required for the iron parts are about 32% of that needed for the gap, calculate the magnetizing current drawn by the motor and comment upon its value. And assuming winding factor to be Kw to be 0.955, efficiency to be at 85%, and power factor 0.85. So these are the data given. For first we will see to it, we will go for the calculation of the flux first. So BAV by pi dl. See, flux we can calculate. See, flux is how much? Flux is ES. ES is equal to 4.44 FTS 5 kWs. This is the universal formula. We have used it in transformers also. The only difference between induction motor and transformer is that this kWs is not there in transformer, whereas in induction motor we have to use this factor of 0.955, okay, because of the construction of the induction motor. So you'll see it is like 400 because what it's saying star delta starting. So secondary would be delta, hence phase and line voltage is same. So 400 only we will take. 400 divided by 4.44 into 50 into 360 into kWs is 0.955. Okay, it is mentioned assuming your, see here, assuming your winding factor kW to be 0.955. So once you are substituting there your 0.955, you get your flux to be 0.0052 Weber. Now your average flux density is P5 by pi dl. P is number of poles is 4. Your flux you calculated 0.0052. Your pi, you know, diameter it is given 0.14 meter. So you can take, and length is given 0.11 meter. So you can take that. So you get your your average flux
Doing
density.
quarters.
Today Ramzan is there. Average flux density is 0.427 Weber per meter square. Diameter of stator. Now diameter of stator is diameter of rotor, because stator is outside the rotor and inside the rotor is there. So it would depend upon your diameter of the rotor plus twice the length of air gap from both sides you have now. So you write 0.14 and length of air gap was 0.5 millimeter. So you have to convert this 0.5 millimeter into meter. So divide by 10 power 3. So when you are dividing it by 10 power 3, so you had 0.14 plus 2 into 0.0005. So you get over here, and this value happens to be 0.141. So gap flux density at 60 degree from interpolar axis is B average 60. This you know that B60 is 1.6 BAV. So BAV you calculated, and you can calculate this value. BAV you have seen 1.36 into 0.043. BAV here you have calculated, it is around 0.427. If you approximate this 0.427, it would be 0.43. So like either you can take that 0.427 also, because you are having calculator, and multiply this with 1.36, so you are getting 0.581 Weber per meter square. So now you have to calculate your ampere turns. So ampere turns would be how much? It would be 80, your 80,000. Okay, that 80,000 kW, LG and BAV, that equation it will be. So that equation which we have derived for your this thing, see here, ATG, wait, it is here, it is ATG would be 800 kg. This they have mentioned. This is what gap correction factor, BG naught, that you calculated. LG it is mentioned. So you'll substitute the values there and get the value of ATG in this equation. So once you are getting the value of ATG, little bit blur, no, not this one, yes. So you are getting the value here. Same equation you'll substitute here, so you get the value of ATG. So you get 18 10 power 3. This is your 5 in 10 power minus 3, 0.58 into 1.25. This is the gap correction factor. This is your LG and this is your KW. So once you are substituting this, because just now you 0.58 you have calculated, wait, this is your BG60, this is your 0.58 that you have calculated, the L and 0.58, your LG value is here, and this is your gap correction factor 1.25. So once you are substituting here, you get a value of 261.57 amperes. Now you have now in the problem it is mentioned, given ampere turn for iron part is 32% of the ampere turn for the air gap. So this is for the air gap, so it is 32% of the 32 divided by 100 is 0.32, and for the air gap it is 261.57, which you just now calculated. This 261.57 into 0.32 would be 83.7. So this 83.7 total mmf required for magnetic circuit now would be your for your magnetic circuit would be normal, that flux gap plus the part for the air gap, because this consists of stator, rotor and core, and this consists of the 5 quantities, and this consists of 1 quantity, that is your air gap. So this plus this would be 35.27, and this magnetizing current would be 30. Magnetizing current drawn by motor would be, now you know that a magnetizing current drawn by the motor is given as 0.427 number of poles ampere turns per 60. This you have calculated. This is 35.27 number of poles, you know, 4. And another thing is your kW, you know, kWs, you know how much it is. You can substitute and calculate your magnetizing current. So this is 0.427, number of poles is P is equal to 4, 86, 35.27, 34.55 in 0.27, kWs given 0.955, TS also given, this is 360. So this happens to be your magnetizing current, 1.7156 magnetizing current value is this. And now your full load current. See, the formula for your current is your power into 3 is output power. Now you need, if you need the current from that very formula, you can write is is equal to, is you can take on the numerator just like I have taken, and you can write P naught divided by 3 es cos phi into efficiency. P naught is already mentioned over there. P naught is 5 kilowatts. So I have expressed this 5 into 10 power 3. Here you can see 5 into 10 power 3. 3 times es is 400. Cos phi is mentioned, power factor 0.85. Efficiency also 0.85. We have to see whether same or not. Power factor. Yeah, see. Efficiency is 85%. The 85% power factor also 0.85. So you have to substitute this and you will get the value of your current. This is your current, how much it is? Yeah. So once you are substituting, you get the value of 5.77 ampere. So magnetizing current as a percentage of full load current. So see, this is your full load current, and that current which you are calculated here is your magnetizing current. This current you have calculated magnetizing current, and this current is your full load current. So magnetizing current divided by your full load current, let's see how much is. So magnetizing current 1.715 and full load current 5.77. So difference is of the motor is satisfactory. For example, this magnetizing current would be 50% or 60% of the full load current. Then is it satisfactory? No, it should be always less than 30% or around that figure for the satisfactory operation of the machine. So now again we will revise a little bit, and again we'll go to the problem. First, in this particular class, what I have seen is we have to calculate the no load current of the induction motor, and the induction motor, again you can see as in the transformer also you have seen by the equivalent circuit which I have drawn, resistance, then reactance, then in middle there was a shunt branch of reactance, resistance, and on the secondary there was resistance and reactance. So in the middle, this magnetizing component is formed by the excitation current, which gets divided into two parts. That is your magnetizing component, that would be I naught cos theta. So So this the core loss is stator teeth, and it can be estimated by the specific core loss. So this is the real loss that is happening in the machine in the form of heat. So this loss is happening in case of per kg of material corresponding to the stator core, stator teeth, air gap, huh? Yes, yes, please. Rotor teeth, rotor core. In stator and rotor teeth, flux density distribution is approximated as a sine wave. So it is like superimposed with the third harmonics, as the actual flux density distribution is a flat top. Flat top means it's not sinusoidal. That flux density gets, if you have to read about this, there is a book by Chapman. You can read about this flat top in transform opposition. I'll just
Sir.
mail to some of your WhatsApp to you. Hello? Yes?
Hello, sir. What is that third
Can you hear?
harmonic, sir?
Hello?
Sir, what is that
Yes.
third harmonic?
What is the, yeah,
What is that third harmonic, sir?
third harmonics, very good. Yeah, just, yes. You stop, I'll explain. Please switch off your mic. Third harmonics is basically what happens is whenever we are giving supply to this induction motor or any machine. So because of the supply in the air gap, our power gets generated in the air gap. What you can see is that deviation from the fundamental frequency is called the harmonic component. So your fundamental frequency, please switch off the mic. Your fundamental frequency is 50 hertz, whereas your air gap frequency now whereas your air gap frequency is deviation from the fundamental frequency. So if your frequency is 50 hertz, your third harmonic would be how much? You only tell me how many hertz it should be, your third harmonic, Rajat? It should be 3F.
3F, sir.
Your fifth harmonic, how much it should be? 5F.
5F,
Your
sir.
seventh harmonic, 7F. Okay. So because of this, see, again, no, yeah, you switch off this. Because of this frequency, what happens is that when your frequency increases, what happens is that your frequency is related to your active power. Your active power is 3V, 3 E5, I5 cos phi. So what happens is that if your frequency increases, so what happens to your current? What happens to the torque indirectly? So they will also it creates a pulsating torque. Pulsating means it will not be smooth. So it will do like that. So noise will come, right, because this noise would be because of the harmonics. To eliminate these harmonics, what we are doing is that we are cutting the stator and the rotor tooth at an angle of 45 degrees, and this phenomena is called skimming. So because of this phenomena, what happens is that we avoid the principle of rolling. And crawling means if we have not cut it at 45 degrees, because of these frequencies, pulsating torque will get induced in the opposite direction. So it will oppose the movement of the machine. And the machine, instead of running, it will crawl at a speed of 1/7. That means if the normal speed of the machine is 1400 RPM, it will only run at 200 RPM, which is of no use, and that too it will be pulsating. So this is the concept of the harmonics in the induction machine. To more understand it, I'm recommending you a book, Stephen J. Chapman, Electrical Machines by Stephen. It's a foreign author, but it's a very easy to understand book in electrical machines. I'll be giving it to Thara or someone. I have a PDF copy of it. Just go through it, read a bit in that, because we have a limited class, and we have to concentrate on machine design part only. So again, you have seen your your magnetizing current and your core loss current, and this I think you did not had any doubt because it's very elementary 10th class. So this is I not, again, core loss current was Im square plus I1 square. Here also, if you can write this cos phi, not what I1 by I naught. Again, you have the magnetizing current. This magnetizing current would depend upon your air gap, stator teeth. Basically what happens is that you give supply to the stator core. Okay, instead of stator core, you are giving supply to the stator winding. Those windings are connected with the core. So once you are giving supply to the stator winding in the stator core, what happens is that a flux is getting established. This stator core flux is linking with the teeth of the stator, which are linked with the rotor teeth, but there is no electrical connection between the rotor and the stator teeth because they are separated by some air gap. So this is the thing that magnetizing component means, is that you are encountering your air gap, then you have your stator teeth, rotor teeth, then your stator core, rotor core. So these are the factors that are linking with your magnetizing component. Whereas the loss component, where it will again happen in the core. See, it will again happen in the core, stator core, rotor core, because in the core only we have seen the loss is happening, or it can happen more loss will happen in the windings, stator windings, rotor winding, because of the presence of some resistive component also. Although induction motor we are saying, but it is not possible theoretically to have a purely inductive material. In induction motor also, we are seeing that we have some amount of resistance. That and transformer also we are saying we have some amount of resistance. Because of having some amount of resistance, there is loss. Otherwise, it will behave like a superconductor. There would be no loss. In superconductivity means a pure inductor is a superconductor. That is it. It is very simple as that. We have an energy storage device also, that is superconducting magnetic energy storage device. What is it? It is a pure inductor. But normally pure inductor is not possible. But now in ISC I was reading some research also. If you are interested in research, they have developed some superconductors at high temperature also. They have established it, some research they are doing it. Earlier it was, if you needed superconductivity, you have to reduce the temperature for 4.2 Kelvin, which is not normally possible in working condition or room temperature for running an induction motor or something like that. So in that thing, if you have a superconductor, what will happen is that your losses will reduce and your efficiency will come as close to 100%. Now, one more thing about this was that also the value of flux density, like it is at, see, there is normally, see, in machines you have an interpolar axis that is called DQ axis, your diametric and quadrature axis, and your it is you seen that the average flux density is 60 degree from the interpolar axis. See, normally your third harmonic would get eliminated at this particular axis, because your maximum flux density happens at an angle. If you see one half cycle is represented by pi, so pi would mean 180 degree, and the maximum value of pi in one half cycle of that sinusoidal, the peak will the maximum overshoot or the maximum peak you will get at pi by 2, because at pi is equal to 0 your graph is starting like this. Your pi is equal to 0, your graph is starting. Then at pi by 2 it would be maximum. Then again from pi by 2 to 180 it is going down. So this value is at pi by 2, and at sine 60 degree into pi by 2 will give you root 3 by 2 into pi by 2 into your average. Like that he is taken. So that average he is getting around 1.36. So this average he is getting around 1.36 from this value, and this 1.36 BAV. So again, to calculate the air gap of the ampere turns at this 60 degree, we have an empirical formula. Now, most of the times I'm using certain empirical formulas. Why I'm doing it so is that can we derive? Yes, we have. There are derivations for this everything. But more, if you see Sahani and all, maybe it's not. Maybe it will not be there, or some points would be there, some it won't be there. I'm teaching you as per the syllabus what is required and what is not required, because we have a large, huge syllabus in this electrical machine design. In one session we study all the four machines, whereas if you see, as far as your machines is considered, you study transformer and DC in one semester, then induction and synchronous in another semester. But here we are studying all the four in one semester, so we have to pick and choose. We cannot do, like according to the examination point of view only I'm teaching. But if you are more interested to learn, I can give you the reference of the books. You can understand those points also. If you want, you can ask me that also. But here in the class, I have some limitations, so straight away I'm written the empirical formula. So this is 80,000 kg BGO and LG, whereas this kg is your gap estimation factor. This is 1.05 to 1.5, and your BGO is 1.36 BAV. LG is length of your air gap. So again, you will substitute these values. Once you are substituting with these values, you get the MMF of stator core. So this MMF of stator core is 1 by 3 pi T plus 2CS plus dCS by P. Similar to this formula we have in the very beginning, we have stated this length, how you will calculate in some of my previous notes. You can just go ahead and just relate to it. So total magnetizing MMF per pole again is given just like in the transformer. Just like in the transformer. Yeah, tell me. Yes, Rajat. Magnetizing current is total MMF divided by number of turns. So 80 divided by root 2T. So the peak MMF related to RMS value is given by this empirical formula, and we'll substitute in the empirical formula. So we get this value. IM is equal to P8060 into 0.427 TS by KW. Then was this formula. Then we looked at this problem. So any doubts you are having, you tell me.
No, sir. No, sir.
Hello?
Sir, share this PDF, sir.
Any doubts, Thara? Huh?
Share
The
this
PDF
PDF,
I will
sir.
send to the Google class. Any doubts you are having?
No, sir. No, sir.
Yeah, I'm sharing the PDF only.
No, sir.
Any doubts you are having, you tell me first.
No.
So, okay, you have another class? You have another class right
Yes,
now?
sir.
Okay. I'm just okay. Do you
Sir,
have
attendance.
okay? I'll conclude the class.
Thank you, sir.
Okay.
Attend
Attendance I'll take from your this thing.
chat.
You have written in the chat from the 33
Yes,
are
sir.
present right now. Yeah. Don't. Yeah. You have one more class right now, huh?
Bye, sir.
Wait. Let me take the
Thank you,
attendance.
sir. Bye, sir.
Don't.
In chat then, sir.
No, I have to. Vivek MG. 1 second. Let me take the attendance first, please. Bear with me. So, what I can say, all of a sudden 34, why it is increasing?
Sir, some network
Okay,
issues.
now
So
how many are there? Okay, bye.
Network is high, sir.
Okay, no problem. So, yeah.
Okay, biಟ್ರು. Let me know. Okay. Bye. Okay, I'm stopping the recording.
Please switch off your mic. Just please.
Please switch off your mic. Please. I am recording.
Hey, class record ಆಗ್ತಿದೆ.
ರೆಕಾರ್ಡ್ ಆಗ್ತಿದೆ